Right, so power, we've kind of already talked about this. Power is a rate. It's a rate of energy flow. And we know that as far as energy goes, energy is charge times the voltage, because voltage is energy per charge. So we multiply by the amount of charge we have. But power is the rate of energy. So when we divide by T, we can see that that's where the V times I comes from. We can also rearrange this a little bit. And so we can make substitutions so that if we just know I and R, we can find power. Or if we just know V and R, we can find power. And so this would be the power that's dissipated when we send current through different devices. And of course, we've already talked about the kilowatt hour too. That's the unit that you buy energy in from our electrical utility. So in general, we assume that the wires that are behind the wall have very low resistance. But it is an important safety factor to consider that, you know, before you haul off and you start nailing stuff into the wall, or you know, putting screws into the studs that are behind the sheetrock, that you have a rough idea about where some of the wiring is going. So usually what happens with the wires is that they snake. If they're going vertically, they're going to snake along studs, which are the supporting pieces of wood behind the sheetrock. And they're usually back at least about an inch or an inch and a half away from the wall. And then the ones that go horizontally are usually down at about the level of outlets. So again, if you're going to start poking holes into things, then, you know, stay away from the region that's about a foot to 18 inches off the floor. And then, because what can happen is that you could nick one of the wires. And when you nick it and cause a separation, now it's not quite as thick as it used to be. So it's going to have more resistance at that particular location. And it could definitely be dangerous. So in order to control the flow of current in our house, we have a number of old style controls, fuses. We still use fuses today, like those meters that you have little tiny fuses. In your car typically has little tiny fuses in it. And they're just, if there's too much current, then it melts the tiny fuse that's inside and it just stops current from flowing. So it is relatively common to blow a fuse in a car. Now, in a house, blowing a fuse is not that great. Sometimes some of the really old camps still have fuses. And that means that you have to have spare fuses around if you're going to fix it. But you don't want to just throw the new fuse in without figuring out what the heck caused it. To make things a little bit easier in our houses, we have circuit breakers. And the way a circuit breaker works is that current flows through the breaker, and we have a piece of metal in there, and the piece of metal is a bimetallic strip. And what happens to it is, since there's two different metals, metal will expand when they're heated up. But if you have two different kinds of metals, one side expands more than the other. And so winds up starting to bend. And if it bends enough and winds up in this little notch that's there, then that is going to open this gap and it's going to shut off the current flow. So for then to reset it, you have to come back. And if you've ever reset a breaker, it really feels like you're winding up a spring. Right? So you wind up this spring so it can happen again. And when they snap, it's usually pretty loud. The downside of this is that these circuit breakers are designed primarily to prevent a fire in your house. And they're designed so they protect the circuit, but they don't necessarily protect humans. And because it takes a certain amount of time for the circuit breaker to heat up. We'll look in chapter 19, we'll take a look at an alternative to that to make people safer, especially in areas where there's electricity and water. So direct current versus alternating current. Batteries, we know, give us direct current. Solar panels give us direct current. And that's about it. So usually when we're generating electricity, we wind up with alternating current because it's a lot easier to generate. So we can model that alternating current with a sinusoidal function, and omega would be the frequency of the oscillations in radians per second. Here in the United States, we can convert that oscillation from radians per second to hertz, and that's 60 hertz. So in the UK, they use 240 volts and 50 hertz, and we use 120 volts and 60 hertz. So in order to calculate power with something that's alternating, we can't just multiply voltage times current because they're going to have a tendency to cancel each other out. So instead, we can do something called the RMS value. If we just plotted current, current would spend half the time positive and half the time negative, and if you average that, you just get 0. So if we square the current and then take the average of this function is going to be 1. It's going to be 1/2 of I0 squared. So this gives us an idea about what the average power is going to be proportional to I and B. But when we take the square root of this to get our RMS voltage, then we have our peak value, I0 or V0, and then we're dividing that peak value, we're dividing the peak value squared by 2. But if we're going to get currents of amps, we have to take the square root. And so the RMS value, which you would use, or we would call just the average, is going to be 1 over the square root of 2 times whatever the peak value is. And this is kind of interesting, just a little connection here about biology. And some of you probably know this propagation better than I do. But it's just kind of interesting the way signals are transmitted in the nervous system. And it's a result of the permeability of cell membranes and the presence of different ions. So essentially what happens is that we trigger a spike, and then that spike self-propagates down the length of the axon. And yeah, so action potential is the amount that's required in order to trigger that. Okay, well, that pretty much does it for the new stuff. And I'd like to spend some time talking about some practice problems. So we're going to look at 30, 34, 36, and 42. And they're going to go pretty quickly. So I'm going to scroll down, and I don't even think they take up very much space. So I'm not going to do this one. Our design thing that we did a few minutes ago ought to suffice for that. And so now let's take a look at the 4 problems that we're going to do. I'll put them together a little more, packaged a little more tightly. So if you want to take a screenshot of this, or maybe you already downloaded the PDF, that's fine. Okay, so I'll give you 20, 30 seconds to take a screenshot. And then I'm going to move them over to my big screen so I can see them. Okay, so I'm going to stop sharing. Just do a little organizing here. Okay, there we go. Okay, so that looks great. We'll take a look at number 30. We have a 2-cent heater at 115 volts. And it's rated 110 watts. So calculate the current through the heater and its resistance. Yeah, we've already did this in our warm-up. So P equals V times I, and V equals I times R. So we plug in the things we know. This is 110. This is 115 times I. Once we get I, we can plug this in over here. This is 115 equals blank times R. Solve for R. So this is quick. So 0.96 amps. And then use that to divide both sides by 115. And 120 ohms. Okay, easy peasy. Doing okay with that? Any questions? No screens for protest? Excellent. Let's try this one, 34. Bang these right out. Again, we're fortunate. We had front loaded a lot of this. 9.5 cents per kilowatt hour, a little bit dated, maybe back in the 90s. But what does it cost to leave a porch light on day and night for a year? So 25 watts energy equals power times time. And once we get energy in kilowatt hours, then we can do the cost piece. So if we're thoughtful about this, then we can put in the units. So we can do less dimensional analysis later on. Like for instance, since I know I want kilowatt hours, let me enter power in kilowatts. So this would be 0.025 kilowatts. And then time, how about I put that in hours? So that would be 24 hours and 365 days. So 24 hours, if I just did that that would be energy per day. And then times 3, make sure I'm doing this right. I want to keep hours, but it's okay. I'm just multiplying by time. So that's 365. Yeah, I'll just put days. I just wanted the dimensional analysis to work out right. So I'll do this, 365 days per year. That'll be fine. Okay, we'll just multiply everything out. So 0.025 times 24 times 365. And what I'm getting here is I get the total number of kilowatt hours. So that's 219 kilowatt hours per year. That's how that finally runs up. And then we multiply it by 0.095. Okay, and that's $28. Good, no screams or protests. That sounds great. We'll go ahead to do 36. And then 42 is really the last one. It's sort of new. So 36, we've seen this before too. Worked on it last time. A 12 volt, 85 amp hour car battery. How much energy is that altogether? Doesn't see what the units are going to be. So it's actually, if we have that freedom, then that's actually really handy because we know energy equals power times time. But power is equal to volts times current times time. So it's these two that when you multiply them, you get units of amp hours. Not SI units. SI units would be amperes times seconds, which equals coulombs. But since all batteries are 12 volts, then we can take the capacity, which is 85 amp hours, and when I multiply those two together, let's see what we get for units. We got 1020 volt amp hours, but volts times amps are watts. So this is 1020 watt hours. And if I divide that by 1,000, then that's 1.02 kilowatt hours. So as we said, not very much, worth only about 12 cents. Okay, so that was just a quick run through these ideas. And you think, wow, this stuff is not so bad. That's what the next chapter, that's where the fun starts. Okay, so just take a look real quick, see if you have any questions. It's totally legit to leave us an answer as kilowatt hours. All right, and then I'm going to reclaim a little bit of space to take a look at that last one, because this is a little bit new. Calculate peak current in the 2.2K resistor that's connected to 120 V RMS AC source. So 2.2, we have a resistance. So that's one of the things that's given. 220 volt. And that's an RMS value. And we want to know what the peak current is. Find I0. Well, I0 would be equal to V0 over R. So I already know that this number is less than the peak value over the square root of 2. Remember, this came from squaring the voltage so that we got something we could average without averaging up to 0. So we took V0 and squared it, and then the average is half of that. And then to get back to units of volts, we took the square root of everything. So that's where the square root of 2 comes from. And so we're going to multiply 220 by square root of 2. So the peak voltage is higher, 311 volts. And then I put that in here. Divided by, express this in ohms, not kilo ohms. So 2200. Now I have I0. An interesting coincidence, right? Right. Okay, so that's a decent set of practice problems for us. Okay, so any questions about that? Okay, good. Well, I have 8 o'clock, and what I'd like to do is go over an assignment that I would like you to try. And the goal of this assignment is to give you some experience trying to think about the variables associated with solar power. And in order to do that, I'm going to start sharing my screen again. So I'm going to just grab this.
Do you mind just repeating what you said? My internet connection just went out and I didn't hear anything.
That's okay. So let me change my camera. I'll repeat it, of course. But I should probably get a little more organized. So I'm going to pull the agenda back over here. Okay, good. I'm going to share my screen so we can take a look at the agenda. And I have a couple of links. So I'm going to beg for your forgiveness because I have a ton of things open right now. And I want to make sure that I share the right screen. Okay, good. So the first thing I want to do is point to the agenda. Okay, great. Scream if you don't see the agenda. Okay, that's good. Not a lot of screaming. I want to take a look at this concept called insolation. And I'm going to stop share and share, and then share this new window because I think it might have opened in a new window. Not sure though. So this website, if you follow that link, is called Solar GIS. And GIS is Geographic Information Systems. But you can, we talked before about the issue with solar energy is that, you know, you have to be in a good place to harvest. So let's start off by taking a look at the world and where are good places for solar energy. Yeah, there we go. So there's a scale down here, and the scale has units of kilowatt hours per day on average. And so dark red colors mean excellent for solar energy. And only land values have been done, which is kind of interesting because, you know, we may find that, you know, potentially floating platforms of solar arrays might be interesting. Although one hurricane can definitely ruin your whole day. So in the southwest parts of the United States, excellent. Northern parts of Africa, excellent. The high Andes Mountains, excellent. The deserts in southern Africa, excellent. Australia, amazing. The Middle East, and they're actually getting on board with solar energy too. So it's definitely recognizing the fact that they recognize the fact that burning oil is not the future. And so they're trying to get into the solar energy pockets as well. But there's an interesting little band right here. This is the equator right here. But we have these two huge continents, and this map is telling us that actually, even though it's the equator, they're not necessarily the best places for solar power. So I'd be curious if you want to write something in the chat if you think you know why that is. Why in these two continents right along the equator does it turn out to not be that great for solar power? Curious to see what you think. I have so many windows open, I don't even know where the chat went. Anyway, it turns out it's rainforests. So these regions experience a tremendous amount of rainfall. And then up here in Vermont, not so good either. So I want to focus on a particular region. So I'm just going to give you an example. I'm interested in doing an off-grid application. And so the region I'm going to select is Africa. So I think that you can see that we have interesting units. So this is kilowatt hours per day. Actually, this is kilowatt hours for the entire year. And the country I'm interested in is right here. Again, it's very green because it's rainforest. This part of Africa, it's sunny for 6 months and then it rains for 6 months. And it rains for even longer here. And the part of the year that it rains is from about June to November, December, which is hurricane season because that's where they start, off the coast of West Africa. And so that's green, and so that's about 1400. So what insolation does, and that's SOL, not SUL, insolation gives us a factor by which we can predict how much energy is available for harvesting. So I'm going to go back to taking a look at Canvas. and take a look at these modules. And I'm going to give you an example of an off-grid application. So let's get to where the assignment is. We've done a lot of little interesting design challenges. And now we're getting to the point where we can handle something I call Go Solar. So here's my example. And it says my off-grid application is a small clinic in West Africa that's running the following 5 devices. And that's what I would like you to have. Now it looks like there are actually more devices than that, but it says I'm going to have 4 12-watt LED lamps. So I'm classifying, even though there are 4 of them, I'm classifying that as one kind of device. And then an autoclave that runs each day for 20 minutes. Remember, when we're calculating energy use, it's not only the power, but it's how long it's on. A 90-watt vaccine freezer that runs 30% of the time. So the running time for that would be 30% of the 24-hour cycle. And then a 60-watt compact refrigerator that runs 25% of the time. And then a 60-watt laptop charger that runs 2 hours a day, 2 hours to charge it. And so if we scroll down, I put in the necessary numbers, and this is in order to figure out how much energy needs to get harvested. So a few classes back, we did an exercise that found out how much your roof is worth. And it turned out it was a surprisingly big number. But that assumes the solar panels are 100% efficient, and they're not. Okay, so based on this, I figured out my daily need is about 2 kilowatt hours. Now, this part of Africa receives about 4 kilowatt hours per square meter per day. That's the insolation factor. And so if I'm going to figure out the power output, current high-performing panels are about 19% efficient, and so that means we're harvesting about 0.76 kilowatt hours per square meter per day. So I just took 0.19 and multiplied by this to get how much is available to get harvested. And so you can see that this is going to tell us how many panels we need, because this is per square meter. So I need to harvest about 2 kilowatt hours a day. But this is saying in this region of the world, we can harvest about 0.76 kilowatt hours per square meter. So I'm going to need more than a square meter, more than 2, more than 3, more than 4, and so I'm going to need about 2.6 square meters. And you can use this, the cost per square meter for this kind of solar panels, about $233 per square meter. So there's another prompt that says, okay, well, if you're going to store that, and the sun doesn't shine every day, so we should probably have like a 3-day supply, especially in the rainy season. And even in the rainy season, we might have to get a generator to charge the batteries instead of the solar panel. So if we're going to store in 1 day, if we're going to harvest enough to store a 3-day supply, then we really need to harvest about 6 kilowatt hours a day. or we need to be able to store 3 days worth. And so this tells me how much energy I can store per battery, and then how many batteries I'm going to need. So you can see it's a pretty big investment in batteries. So the theory is that since you're harvesting energy at almost no cost, then you can take the value of that energy that you're harvesting over time, and then figure out how much time do you need to be harvesting energy before the value that you get from that energy is actually equal to what your investment is. It's a little while. Okay, so I'm going to get away from this example. I'm going to go back to modules, and I'll show you where the prompt is. So I'm going to scroll down, and it's a PDF. And so I'd like you to have fun with this. You could, really imagine anything. Like maybe it's some kind of pole barn in the Northeast Kingdom, because you want to run off there with your horses and never see another human again. Or, maybe it's something related to healthcare. Maybe it's a school. Maybe you want to, take some time off and join the Peace Corps and go build a bunch of schools somewhere. So this information is actually in the chapter 19 module, and it's just called Go Solar. So that's the prompt right there. It's a PDF, so you can download it. And you can download my example as well. And then the PDF is going to have some hyperlinks in it, so you can check those out. And if we were like regularly in session, I have this nice little slideshow that shows you where our house is in Liberia. We actually have a couple of houses there. And my wife, Mary, was born in Liberia, and we met when I was a Peace Corps volunteer, and she worked for Peace Corps in Liberia. So when I came back with a little more than just my luggage. And then she's been back there several times, but the last time she went was February, and she planned on spending a month there, but then it happened. So she didn't get back home until July 7th. But fortunately, she had a house there, and she had a bunch of solar panels, and she had a good time and was well taken care of, but she got really bored. Didn't we all? All right, so I'm going to stop sharing, and then give you a chance to ask questions. Yeah, there we go. Yeah, some good guesses. In terms of the timeline, I'd like you to just think about a possible application. So you got a bunch of stuff to work with. I'm going to see you in person on Tuesday. If you really want to see some of the slides, I'd be happy to show them to you then. But it is getting a little bit late, so I just want to be conscious of that. And Chapter 18 quiz will be posted, and I think what I'm going to do is, I think we're going to, 18 is pretty straightforward. So I think what I'd like to do is give a trial version on mastering physics. So I'm going to go back and check and see if anybody still needs access codes. I think I've got almost everybody signed on, but I'm going to generate the quiz in mastering physics. And I'm going to turn on multiple attempts. So you'll have multiple chances to try and respond to questions. So we'll see how that does. All right. As far as due dates for all this stuff, like I said, just try and bring an idea for this off-grid application on Tuesday. And then I will have the quiz uploaded this weekend, but I won't ask for it to be due until the end of next week. Just anticipating that there might be some issues with mastering physics. So we're going to give it a trial run and see how we do. All right. Any questions that anybody has? Okay, so I don't see any questions, but if you do want to talk in a smaller group, I'd be happy to stay on. That's it for tonight. Don't forget, we're in person at CCV Tuesday night starting at 6 o'clock, and tons and tons of interesting stuff to do.
Looking forward
Thank
to it.
you.
Yay.
Thank you. Have a good night.
Yeah, thank you.
Thanks
Bye,
for your
Anna.
Have a good night.
Betsy.